You've heard about Bob Fugate from Pete Kluper's talk, but I'm going to introduce him again. Robert Fugate is internationally recognized as the first to demonstrate the concept of laser guide star adaptive optics and to develop and apply those technologies to make the concept practical on contemporary large ground-based telescopes. This technology allows researchers to overcome the limitations on image resolution set by the Earth's atmosphere and makes essentially a quantum leap, to use a cliche, in astronomical observing resolution. Dr. Fugate has spent over 35 years at the Air Force Research Laboratory and retired from there as a senior scientist for atmospheric compensation 11 years ago. He created the Starfire optical range, which is in use to correct atmospheric effects in the propagation of light. He championed the transition of this technology from the DoD to the astronomy community, and he's an advisor to the Air Force and other government agencies you can imagine, and private organizations. His latest endeavor is serving on the advisory board of the Breakthrough Starshot, as are about 10 people here, actually. And he's the chairman of the Laser Subcommittee, which has just released its request for proposals for research on the Starshot laser system. His title today is the Starshot Propulsion System. Please welcome Bob Fugate.
Okay, thanks, Jim. Some of my early charts here were already discussed, but I wanted to tell you, again, briefly what the objectives are. We're sending a lightweight sail with a chip attached, and we need to go fast, and that's part of the issue here. Here is another shot of the star chip, and laser beams are the wind, and it's already been mentioned that Robert Forward significantly introduced this idea back a generation or so ago, and one of the things he said was whether it can be engineered and is financially or politically feasible is left for future generations to determine. And I said, we have arrived at those future generations. So the things that have happened in the meantime that make this enticing now is miniaturization of electronics, obviously, nanomaterials, nanotechnology and metamaterial type sails, materials in general, fiber laser technology, integrated photonics. We haven't said much about that, but it may be possible to build this photon engine out of very small semiconductor type lasers on chips and do all the processing that's needed to do that. People have envisioned, for instance, just a big flat plane of many hundreds of acres full of laser diodes and no optics. And in theory, if you can control the coherence of those and point them in some way, you can control what's in the far field. There has been a lot of work done principally for the Department of Defense related to phased array technology. Most of that technology has been in an area that we call tiled arrays, where you have a common surface that gives you a reference for the piston phase and makes things much easier. But these are advances that we now need to take a look at in terms of this project to determine, is this the right time to move forward? Kevin more than adequately covered the topic of light pressure and how pushing on a sail with a laser works. I just put up, and again, I'm not going to show this because His material is much more detailed. This actually comes from Phil Lubin's calculator that's online, which is fairly easy to find on the internet. So here are the top level sort of derived requirements for the Photon engine, 50 to 100 gigawatts. Being able to launch once every day, once every 24 hours, several hundred seconds of runtime. The wavelength here we have just because it transmits well in the atmosphere. 1060 plus or minus 20 is kind of a tight spec, but actually, you know, we're even looking at 2 microns, especially for fiber lasers, because they're you know, somewhat forgiving in terms of some of the nonlinear effects we see for single frequency lasers at high power. But you know, you can even imagine going to shorter wavelengths, although the atmospheric problem gets much more difficult. So we're open to ideas on whatever wavelength. 1 to 5 kilometer output aperture, Earth-based in the southern hemisphere, and we're hoping to get 50% of the output power onto the sail. We think 30% is what's needed. And the absolute pointing, we have to account for the proper motion of our target star, and we'd like to arrive within 1 AU. I think we understand for the Centauri stars what their proper motion is to 5 or 6 decimal places, so that's not going to be hard, but we have to track the star and figure out a mechanism for pointing all these individual apertures in the phased array in the direction, in the so-called point-ahead direction, if you will, to lead where we need to point the laser, get the sail going so that it's where the star will be 20 years later. You know, we're still looking at what the elevation requirements are for the array. We'd like to go higher because the turbulence is easier to deal with. We have more transparency in the atmosphere, you know, less absorption and scattering losses and so forth. It's going to be difficult to get a large field of regard with this large an array. Maneuvering all the individual elements of the array over big angles is contradictory with trying to make the array compact, to make it have a large fill factor. And the beam jitter, the coherent beam jitter gets really a tight spec, but all we can do in the array is point each element to a fraction of its diffraction width, lambda over d, roughly. And if we do that and make the array coherent, then diffraction and the laws of propagation take care of themselves. The beam profile will be very important because of stability of the sail in the beam. As you've heard earlier, we expect the sail to ride in the beam because we really have no way to get feedback from what the sail is doing and make real-time corrections. I mean, at the longest ranges, the round-trip propagation time is a minute or more. So that's not a very good control loop. And we also, because of the accommodation of proper motion, it's kind of a catch-22. The direction in which we point the laser, and hence the sail, depends on its final velocity. And whereas we don't know that until we're done accelerating. So we have to kind of assume that everything's going according to plan. But we think we need the final velocity knowledge to within 1.5%. But it may be that the sail is autonomous enough that it can do its own mid-course correction based on knowing where the target is, knowing where it is in relationship to, like, the sun. So what are the biggest challenges? The number one challenge, as we see it, is constructing an architecture to coherently combine what is essentially an unlimited number of lasers in an array that's kilometers in size. I mean, this is a problem that nobody has tackled before. So, you know, if you had 1 kilowatt fiber amplifiers, you need 100 million of them. And you need 100 million telescopes. If you have one for each laser, or maybe you need fewer than that telescopes, depending upon how big they are and how big the total array size is. So the issues, I'll show you what you really have to do in order to do this in the next chart, but that's the number one problem. So we do have, we've run into a wall in terms of sort of a Moore's law for fiber laser power that's of high quality. Yeah, you can buy a 10 kilowatt fiber amplifier, but it has a very broad spectrum because at single frequencies, once we run into the nonlinear effects of things like stimulated Brion scattering in the fibers, we can't go any higher in power. The only way to do that is to introduce more wavelengths by spectrally broadening the seed laser. And so that makes the coherence length short. And you'll see that if you have an array that's like 3 kilometers square, for instance, and you look at the corners of the array to the sail, the path length difference approaches 1 kilometer. So it's just based on geometry. So you can reduce that a little by maybe building the array on the side of a hill if you're, off the zenith, which you will be. There's no place on Earth where there's land at minus 62 degrees, which is the declination of Alpha Centauri. So you're either going to be in a boat if you want to be directly under it, or on the side of a hill or something like that. We're also then very interested in the development of high-power, long coherence length fiber amplifiers. And I'll show you one concept which may work for that. Some of the other challenges, and really those first two are the subject of this first RFP that we're releasing, or the main subject. So the other thing is we need to be able to generate a profile at the sail, and as the sail moves away, we need to keep that profile. So that means we need to keep changing the amplitude and phase of all the elements of the array to do that if we're really after a designer profile, and I'll show you a notional idea in a minute. Kevin talked about what is essentially a truncated Gaussian, but if you had a spherical sail that was gas-filled in that beam, for instance, it probably isn't going to be very stable. And if we get any transverse motion of the sail, it's just going to zip right out of the beam, and we may not know about that, or if we have some auxiliary sensor that's watching returns, it'll be too late when we once find out about it. The array has to have a high fill factor. We're not allowed to separate these apertures because, the whatever you get at the sail is nearly the Fourier transform of what you have in the pupil, and all that power is going to go into the side lobes and not on the sail if we start making space between them, and roughly proportional to the ratio of the ratio of the area of the encircled array to the actual area that's coming out of the lasers. We would like to have a large field of regard, especially if we're doing prototype missions like in the solar system, so that we, instead of just being able to point south at 62 degrees zenith angle that, we can point in some other directions to send prototype sails to other objects in the solar system. And the whole business of, acquiring the sail and ramping up the power and, capturing it, tracking the target star. Can we do it, for instance, in the daytime? Proxima Centauri is a 12th magnitude red dwarf, and tracking it with the precision we need to do, 5 decimals of point ahead may be difficult, especially if the apertures are small. So those are some of the big challenges. I'd just like to point out that up until now, people that have been phasing lots of lasers, lots meaning a few dozen, have had some sort of a reference, like in the middle diagram here, the red button. In this approach, you have a common aperture, and so you can relate the piston between the various elements of different lasers easily. You may also have reflections from the target. We're not counting that out. We've done some estimates about how big the signal is from the target, from the sail coming back. And but remember, if you're trying to share the aperture with that in order to do things like atmospheric correction, you have maybe tens of kilowatts going out of that aperture, and you have a handful of photons coming back. And oh, by the way, it's Doppler shifted. How useful is it in terms of doing phasing of the array? To be determined. So really what we have is the bottom diagram where we have a lot of separated telescopes. What we really need is some sort of a common reference. So maybe we have a cooperative beacon that is part of the mothership, or because they're in orbit, they're moving away and we can't get too far away from the direction that we're firing the laser to use the beacon. So maybe we have a series of those in orbit that are coming by. This sounds all expensive and complicated, but I think it is probably not as expensive as $100 million 1 kilowatt lasers being phased up on the ground. So one way to think about this is these elements in which we have a seed laser here, which is then divided up into a lot of copies, maybe 100 million, and distributed to elements that enable us to control the phase of those arriving signals out of those kilometer-long distribution fibers. Also, there's going to be noise in those fibers, and phase noise. It's changing in piston, all in a random way at some high frequency. So we need to be able to sense that for every beam train and correct it with some sort of a phase shifter. Then we would have amplifiers, some sort of way to direct the tip and tilt of the outgoing beam. And out here we would have a tracking reference from our star, maybe reflected light from the sail, at least maybe initially, and a beacon that enables us to measure what the atmospheric turbulence is. So, and each channel, each element of this phased array, those are the kinds of things that we need. So the signals that we get back in terms of control are then used to adjust, for instance, the piston phase back here with this phase shifter. So that includes, the phase noise in the fiber. It includes the optical path length change through the turbulent atmosphere. And it also includes, things that we aren't even thinking about. So here's what we have to do to phase things. If we look at two parts of that diagram from before, here's our master oscillator, our seed laser. And so it has some coherence length. It's some sort of temporal coherence over which, if we were to divide that up into separate beams and then interfere them, as long as we're within the coherence length, we can do coherent combining by adjusting the phase carefully. So, but if for some reason there's a large, let's say the coherence length of the laser is 1 meter, that means that if I pick a part of the beam and delay it by less than 1 meter, and then I recombine them, I can get, by adjusting carefully, the phase of the two beams, I can get constructive interference. But if I delay them much more than 1 meter, or even 1 meter, that constructive interference rapidly fades away. And if I'm looking, for instance, like in a Young slit experiment at fringes, I have no contrast in the fringes. So I cannot combine these beams if they're far outside the coherence length of the seed laser, if the path difference along each one of these. And like I said, the path difference between corners of the array for the sail being on the axis of the array but off some zenith angle is like 1 kilometer. So one way to do that would be figure out some way to adjust all the path lengths to all these, let's say, 100 million lasers, during the time I'm accelerating the sail over like a 2-degree engagement. That doesn't seem very practical to me. So the next best thing is to use a laser that has a very long coherence length. And that's one of the things we're asking about, is how much power can we get out of very long coherence length lasers. So here's a little diagram, which is probably not needed, but imagine this square is the array, and we orient it to point. So all of the, as we see it, we accelerate the sail when it crosses the meridian and due south. And so if I just calculate what is the path length from this corner of the sail, or the array, and from this corner as a function of the zenith angle, that's what I'm showing in the next chart. And depending upon the size of the array, you can see that this is 100 meters, 1,000 meters, 10 kilometers. And so for a 3-kilometer array at 20 degrees, I'm at 1 kilometer. And it changes about 50 meters during an engagement. So these are important issues in terms of what kind of lasers you can use in the array in order to make the whole array coherent. So if we make the array sparse, the power goes into the side lobes. And here's a very simple example. These are Gaussian beams, and here they're arranged in a hexagonal close-packed array, so that if I had hexagonal lenses, for instance, that were butted up next to one another, and I had a Gaussian beam or near Gaussian beam coming out of my fibers, for instance, to illuminate each one of those lenses, I would get this result. This is the fraction of the enclosed power in a bucket, if you will, as a function of distance from the axis. And here, where I've moved the apertures just 1 diameter apart, I've lost about a factor of 3 in terms of on-axis power at the sail. So, the challenge of keeping the array compact and being able to point it is really hard, because this thing is 3 kilometers in diameter. If you build a big giant 3-kilometer thing and try to move it around, that's going to be really hard. Maybe it's not out of the question. If you build really big apertures and have fewer of them and use adaptive optics, the system gets a lot more complicated. If you can keep the size of the sub-apertures about the coherence size of the atmosphere. The Fried parameter, called R0, this is basically the size of a telescope that produces a diffraction-limited image. Then all I have to control is tip, tilt, and piston over each aperture. I say all I have to control, that's still a lot. So we know that on the ground at the best C sites, we can count on R0 going from maybe 10 centimeters up to 25 centimeters. This is as it's measured in the visible, but we get an advantage by going to 1 micron, for instance, since R0 scales up as lambda to the 1.2 power, lambda to the 6/5 power. And so that allows us to build bigger apertures at longer wavelengths. So here's a cartoon of if I built my subapertures at 10 centimeters, kind of what they would look like, and if I built them 50 centimeters. And shown sort of notionally underneath is stuff we need like sensing for doing tracking and tip-tilt control, for doing some sort of computations perhaps, and for doing thermal management. So we might have energy storage and cooling underneath, distributed. Building big energy storage facilities, we kind of know how to do that, but one of the issues is the discharge rate. We don't know how to get that much energy out of a big storage facility that quickly and distribute it. So it's better to just maybe have batteries under each one of these. So in looking at the single frequency high-powered amplifiers, we're kind of, so this is line width in terms of kilohertz. We'd like to get down to 10 kilohertz, maybe better. But we'd like to also get the power up to maybe a kilowatt or better. We even have people telling us 5 kilohertz at 5 kilowatts. And so this is just a chart of how much power we can get out of these single frequency amplifiers. You might see charts that go, that look like they're going up and we're not going to have any problem, but if it's single frequency and long coherence length, we do have a problem. So that's a challenge. One of the approaches that has some promise is something called a photonic bandgap fiber amplifier. This is work done at Clemson University, sponsored by the Air Force, and it holds some promise of being able to advance the ceiling in terms of power and single frequency operation. So I mentioned a designer beam profile. You can sort of get the idea here that if we had a spherical sail, as an example, and we had a beam that was bright around the edges and not so bright in the middle, that it might ride in that potential well in a stable way. So while this is theoretically possible, it's extremely challenging because we have no feedback from the sail. We would have to do all of this in a feed-forward kind of way and predict where the sail is at whatever range so that we could make the beam that size at that range. One thing we might do is we could monitor how fast it's going by maybe having an aperture off to the side and watch and have a high-resolution spectrometer there so we could look at the Doppler shift of the returned light and use that as a speedometer to see how fast the sail is going. But as time goes on during the acceleration process, that information gets older and older because of that dang thing about the speed limit on the speed of light. So what are some of the longer term issues and challenges? Cost is probably the biggest one. Kevin showed numbers in his charts that are considerably way cheaper than anything we can get today. So that's something that really needs to work on. Site selection is not super critical, but it's longer term. The energy production and storage and discharge we think is a solvable engineering problem. Again, I mentioned the acquisition, pointing, and tracking of the mothership, the sail, and the objective star, and how to do that accurately. And really, there's probably trades on what the orbit and beacon, definitely the beacon design for if a beacon is used. What we really need is some really great way to do all of this, in a much simpler way than what we're thinking now. There's lots of issues related to space policy. If you have a 100 gigawatt laser, that's going to attract some attention and require some controls, and we have to be careful not to vaporize anybody's satellite. We are just in 3 phases over the next 5 years for the Photon engine. The first phase is concepts and analysis. It's a paper study. The second phase is if we find something useful in terms of concepts, we'd like to build some lab hardware to validate those concepts. And then in the third phase, we'd like to take those in the field in a representative turbulent atmosphere. And we're releasing, as Pete mentioned, we're releasing the phase 1 RFP this week. So if anybody here has the solution for this phasing issue, please let us know this afternoon so we can get on with this. Any questions?
Please use the mic.
Is this the capsule, so to speak, on a rocket?
Yeah.
So it's not, you can use just a regular old NASA rocket, but the key is the payload that launches the sail.
Correct.
Okay.
I think we use Elon Musk BFR.
So you mentioned the problem of the length of the beams as the target gets farther away from
Yes.
the array. Could that actually be used to create that hollow beam profile that you're describing?
Yeah, if you look, for instance, at maybe just defocusing the beam, that's not a very nice looking beam. It's full of rings and all kinds of stuff. So I think more control than just a global defocus would be needed.
Okay.
But yeah, it's easy to make holes in beams, in the centers of beams, but the rest of the beam looks really pretty bad.
Thank you.
I have a dumb question. I'm running the exhibit design workshop, and that's my role in life. What's the advantage of a short pulse versus a longer, more continuous laser pulse to accelerate slowly?
Well, it's a trade, as Kevin discussed. If you want to go longer and control the shape of the beam at a greater distance, for instance, you need a bigger and bigger array to stay within. There was a discussion about the near field and the far field. The near field is roughly d squared over lambda, where d is the diameter of the array. And so if you want to be able to control what the beam looks like on the sail, if that's really a requirement, then the bigger the array gets, the longer you can go and the longer you can laze. And so that's all a very complicated trade that Kevin certainly has the handles on.
A short follow-up. In the spherical sail, where is the chip located?
That's a good question. Who has that answer?
It is assumed to be on axis in the middle, therefore requiring some guys to hold it in the center. And as we will see in the next talk, that then can move around. There's some elasticity, and so you've got some motion of the sail, but also the payload relative to it. And that's true in all sail designs. No more questions? Thank you.